Cutting tool nomenclature. There is a picture. From this picture, we can learn different types of angle. And note that all the rake and clearance angles are measured in normal direction. Side rake angle, we describe it as gamma x. Next one, end cutting edge angle, phi e. Side cutting edge angle, phi s. Back rake angle, gamma y. Side clearance angle, alpha x. Nose radius r. And end clearance angle, alpha y. Cutting tool nomenclature. Side cutting edge angle, phi s. The side cutting edge angle is usually referred to as the lead angle. It is the angle enclosed between the side cutting edge and the longitudinal direction of the tool. The value of this angle varies between 0 degree and 90 degree, depending upon the machinability, rigidity, and sometimes the shape of the workpiece. Usually, the recommended value for the lead angle should range between 15 degree and 30 degree. Next one, auxiliary or end cutting edge angle, phi e. The end cutting edge angle serves to eliminate rubbing between the end cutting edge and the machined surface of the workpiece. Although this angle takes values in the range of 5 degree to 30 degree, commonly recommended values are 8 degree to 15 degree. Cutting tool nomenclature. Side clearance angle, alpha x, and end clearance angle, alpha y. Side clearance angle and end clearance angles serve to eliminate rubbing between the workpiece and the side and end flank, respectively. Usually, the value of each of these angles ranges between 5 degree and 15 degree. Next one, back rake angle, gamma y, and side rake angle, gamma x. Back rake angles and side rake angles determine the direction of flow of the chips onto the face of the tool. Rake angles can be positive, negative, or 0. Its value usually varies between 0 degree and 15 degree. Last one, nose radius, R. Nose radius is favorable to long to life and good surface finish. There is an improvement in surface finish and permissible cutting speed as nose radius is increased from 0 value. Chip formation. Every machining operation involves the formation of chips, the nature of which differs from operation to operation, properties of workpiece material, and the cutting condition. Chips are formed due to cutting tool, which is harder and more wear resistant than the workpiece, and the force and power to overcome the resistance of work material. The chip is formed by the deformation of the metal lying ahead of the cutting edge by a process of shear. Four main categories of chips are discontinuous chips, continuous or ribbon type chips, continuous chip built up edge BUE, and serrated chips. Types of chips. First one, discontinuous chips. These chips are small segments which adhere loosely to each other. They are formed when the amount of deformation to which chips undergo is limited by repeated fracturing. Hard and brittle materials will produce such chips. Second one, continuous or ribbon type chips. In continuous chip formation, the pressure of the workpiece builds until the material fails by slip along the plane. The inside on the chip displays steps produced by the intermittent slip, but the outside is very smooth. It has its elements bonded together in the form of long coils and is formed by the continuous plastic deformation of material without fracture ahead of the cutting edge of the tool and is followed by the smooth flow of chip up the tool face. Types of chips. After the previous video, first one is continuous chip built up edge. This type of chip is very similar to that of continuous type, with the difference that it is not as smooth as the previous one. This type of chip is associated with poor surface finish but protects the cutting edge from wear due to movement of chips and the action of heat causing the increase in tool life. The last one is serrated chips. These chips are semi-continuous in the sense that they possess a sawtooth appearance that is produced by a cyclical chip formation of alternating high shear strain followed by low shear strain. This chip is most closely associated with certain difficult to machine metals such as titanium alloys, nickel base, and austenitic stainless steels when they are machined at higher cutting speeds.